Yeah, our lecture today covers the basics of shear force and bending moment. Across a beam, depending on the distribution of a force, even like if I consider a very simple example that I have a support here, another roller here, and I put a 10 Newton force here. The distance from here to here is 3 meter, and then from here to here is 3 meter. I like to find the distribution of shearing force. Let me just make this like instead of 10, make it 100 Newton. So I have 100 Newton force pointing down, A here and B here. I like to find the distribution of the shear force and then bending moment across this beam. Before I move on, I need to find the ground reactions. And in this shape, if you consider, like for instance, one ground reaction here as FA or RA, and then one ground reaction here as FB, if you look into the beam, you can simply say this is in the middle, so FA plus FB is equal to 100. So remember those three equations from statics. So sum of f of x equal to 0, sum of f of y equal to 0, and sum of moment equal to 0. Sum of f of x, I don't have any force on the x, and basically there is an ax here which make that ax 0 because there is no force on the x. Sum of f of y equal to 0, so this equation will give me fa plus fb minus 100 equal to 0, and then sum of moment. When I say sum of moment, you can ask me about what point. That's because it's important. I'm going to assume about point A is equal to 0, and then again, moment about any point should be 0, not even about point A, but any other point. So in this case, I have 100.3. That's going to go clockwise. A minus there, plus FB into 6 equal to 0. From here, I'm going to get FB is equal to 50. I already knew it is 50. I just did the calculation in case the force is not in the middle, right? It's somewhere here that you need to do the calculation. So FB is 50, you put in this equation, you're going to get FA is equal to 50. Now, each of these forces are 50. What I'm going to do, I'm going to do a cut from different places because I want to draw a diagram. So if I want to draw a diagram, I should have a reference point. In this case, I'm assuming my reference points start from here. So this is going to be the reference point, and X is going to go like this. So I will start doing multiple cuts to find how much the shearing force and bending moment at each location is. Remember from our lecture on internal forces, if you break a part of a beam, you will end up at 3 forces. And those 3 forces were, again, I'm going to have like another piece here, assuming that I cut it from both ways. So you're going to have a normal force. We have a shearing force. This is V. So N stands for normal force. V stands for shear force. And we have a bending moment. So whenever on this beam, wherever on this beam I cut, I have to put these 3 stitches in there. Because this lecture is about shear force and bending moment, assuming that there is no force on the X, so I don't need to be worried about the normal force. I just be worried about the shearing force and the moment. So if I start from this point, from here to here, there is nothing in between, right? Except there is a force there. So I'm going to cut it from somewhere here. If I cut it from somewhere there, I can have the first cut, again, the first cut, assuming that I have the first cut in position 1. On the position 1, I have something look like this. I have 50 going up here. That's actually reaction at A. And then down here, I'm going to have a V. And then a bending moment like this. And the distance from here to here is X because I cut it at distance X. So I can do sum of f of y equal to 0. Sum of f of y equal to 0. From here, I'm going to get V plus 50 equal to 0, and V is equal to minus 50. So from any point, from point A to point in the middle, for this section 1, everywhere that you cut, the V is equal to minus 50. Now for the moment, if I do sum of moment, I need to consider a point. I'm going to consider the point here or the point here. It doesn't matter. Wherever point you are more, again, easier for you to understand, use that point. If I do a moment about this point, I have the M plus, again, I'm going to assume that this is like a point C. Sum of moment about point C equal to 0. I have the moment, and then this one, FA, into this distance. That's actually clockwise. So I have M minus 50 into distance X. Again, X is keep changing from 0 to 3. So it will be minus 50X equal to 0. M is equal to 50X. Done with this. I need to have like another cut. The other cut that I do is I do the cut after the 100. I'm going to have a V, a shear force, a bending moment M. I have 100 here going down. The distance from here to here was 3, and the overall distance from here to here was X. And the ground reaction here, FA, is 50. So I will repeat the same equation I repeated there. Sum of f of y equal to 0. From here I have 50 going up, minus 100 going down, plus v is equal to 0. From here I'm going to get v is equal to positive 50. Then for sum of moment, I'm going to do about point D equal to 0. This is assuming this is point D. So I got the M, and then this force create a positive moment. So plus 100 into the distance from here to here. The whole distance is x, that's 3, so it will be 100 into x minus 3. Plus, in this side we have the whole x, 50 into x. So I'm going to start simplifying the equation. So in this case I'm going to have I have like 100, then so M is equal to, so 100 times 3 will be minus 300. You bring it to the other side, this will make it positive 300. So it will be minus 50x plus 300. That's what I got. So 3 times this is a 50x, and that one actually created clockwise. So that was actually minus 50x down here is equal to 0. So you brought it to the other side. This will be this equation. So I like to draw my diagrams. So to draw the diagrams, let's start with the first one. I'm going to draw the shear diagram, and then underneath that I'm going to draw the moment diagram. So this is the diagram for M, and this is the diagram for V. So V is, again, I needed to put some distances in there too, because V has a negative portion to it. So I'm going to just assume the V is here. And then this is the X. Down here is the X as well. So 50 from 0 to 3. So V from 0 to 3 was 50. So let me use a different color so you can see it. From 0 to the 0.3 meter, the amount of V was simply 50. That's here. Sorry, minus 50. This is minus 50. And from this point on to here was 50. So the only thing, the sign changed, right? Because on one side your shearing force is up there, the other side shearing force is down. The amount of it remain as 50. For the bending moment though, so in one side we have something like this. We have a line which is 50x. up to point 3. From point 3 after, we have minus 50x plus 300, right? In this equation, you have to draw that line. So I have the line at minus 50x plus 300. If I evaluate this, again, 50 times 3, this point up there is 150. If I put 3 in this equation, I'm going to get again 150. So the line here, again, if you put 6 in this equation, you're going to get 0. So if you draw the second line, it's going to look like this. And that's the line of minus 50x plus 300. And this is the diagram that I have for the force, minus 50 to 50, and then that's for shearing force, the bending moment. So let me just do one more example, then we'll start doing some coding, and then grab into like a more complex types of examples. In the other example I have a beam like this. Point A, point B. I see I have a roller here. I have the length in this case as 10 meter. Instead of having a point force, this time I have a distributed load. I have a uniform distributed load. Something like this. And then given to me, the amount of this force is 60 Newton per meter. As you know, uniform loads, again, majority of the loads that we work in reality, they are uniform loads. We don't have a point force. If I apply my hand like this is the distributed load. The load is distributed over an area. This is a 3D. In 2D is over a line. That's why the unit is 60 Newton per meter. As we discussed in statics, you can convert this to a point force to find the ground reactions. Let's do that first. If I do that, I'm gonna replace this loading with one point force, and that force I'm gonna put it in the middle right here. The amount of that will be the area underneath this, so which is gonna be 60 times 10, and the answer is 600 Newton. Just keep your eye on the unit. 60 Newton per meter times 10 meter is going to be 600 Newton. So I put it on the middle. So 5 meter from here and 5 meter from here. I have the FA here, reaction at A and reaction at B. So what I could do, I could say again, it goes back to the similar example that I did a moment ago. So you just go with sum of f of x equal to 0, nothing on the x, by the way. Sum of f of y equal to 0, and sum of moment I'm going to do about a is equal to 0. This will give me FA plus FB minus 600 equal to 0. So you get FA is equal to 300, FB is equal to 0. Remember, because it's in the middle, right? That's why I get it. If it was closer to here, you have to go to this equation to find that. After I found FA, FB, I'm going to go back to drawing my diagrams. This time, the reason that I have a uniform load, this has helped me. I just need to do one cut at the distance x, and I can set up my equations easily. So I'm going to do a cut at the distance like x here. If I do a cut at distance x, I'm going to have something like this. I have the force at A, which is equal to 300 here. At this cut, I have a shearing force V and a bending moment like this. I cut it at the distance x, and this distance x, we have a uniform load, and that uniform load is 60 Newton per meter. So I'm going to do sum of f of y and sum of moment to find this v and m. So sum of f of y equal to 0. From here is going to give me v. I got stuck because I don't know what I'm doing. This is like, again, 60 distributed load. I need to replace that with one point force. To replace that with 1 point force, I'm gonna, because this is a uniform load, you're gonna put it in the middle, right? And then the amount of it is the area under the curve. Area of the curve is 60x. So it will be 60x, and then where I put it distance of half of x. So I'm going to say sum of f of y equal to 0. From here, v is equal to v is equal to minus v plus f of x, which is going to be 300, plus 300, and then you have this force coming down, minus 60 x equal to 0. From here you get v is equal to minus 300 plus 60 x. That will be the shearing force, and all left I need to find the bending moment. So sum of moment about point C equal to 0. I'm guessing this is point C. So I have the m, I have this force that's going to go counterclockwise, and the force 300 is going to go clockwise. So plus 60x into half of x. Okay, this distance is half of x. The force pointing down is 60x. And then I have the 300. So the 300 is going to go clockwise, minus 300. That distance is x is equal to 0. So if I simplify this equation, I'm going to get m is equal to minus 300 x squared plus 300. Sorry, that's what the first one will be 30. This is 60 divided by 2. So minus 30 x squared plus 300 x. Now x will be going from 0 to 10. I want to draw the diagram for the force and draw the diagram for the load. Usually we stack them on the top of each other. There is a reason that I will go over it in the next few minutes. But the diagram for V, X and V, we start from, we want to evaluate it. So at the distance from 0 all the way to the distance at 10. From here to here. In this equation of V, if I put 0, I'm going to get minus 300. So I'm going to start from minus 300. And then if I put, this is a line, right? You can evaluate it at different location. So one, I put x is equal to 0. I'm going to get v is equal to minus 300. Next time I put x equal to 10. I'm going to get v is equal to positive 300. So I go from minus 300 to positive 300. It looks like a line. And that's going to be something look like this. In the middle, at the distance of 5, I intersect with that point, and I reach to 300 here. Not too difficult. So let's do the moment. The moment is a quadratic equation. Quadratic equation, you need to pay attention to some more stuff. Like for instance, if you reach to a maximum, you go to a minimum, something like that, right? So if you put x equal to 0, you're going to get 0. So your moment at 0 is 0. And then if I put x equal to 10, so I'm going to get minus 3,000 here, plus 3,000. So if I put x equal to 10, I'm going to get m equal to 0. What's going on? So you go to a curve, like you go up and then you go down. So basically the curve for the moment is going to look like this. Again, if you are curious to know what the maximum of this curve is, you can do actually the first derivative of this. If you do the first derivative of this, you will get m prime equal to 0. From here, I'm going to get minus 60x plus 300 equal to 0. And then at x equal to 5, I reach to the max. If I evaluate it at x equal to 5, I put x equal to 5 in that equation. I'm going to get m is equal to minus 30 into 5 to the power of 2 plus 300 into 5. And I'm going to get 750. So 750, that's your maximum bending moment. If I want to design for this case, if this is a table and you have a distributed load on the top, you will design it for the maximum bending moment, right? You have the maximum bending moment in the middle, and this thing, if it wants to break due to shear force, it's going to break either at A, either at point B. That's where I have the maximum shear force. So the third example I have an example of a triangle before I move on to a more complex shape. So on the triangle, I have a triangle look like this. Again, I try to make them easier because right now we are just solving examples. I have a distributed load, but this distributed load this time is a triangle. Now, the height here is 50 Newton per meter, and the length here is 3 meter. Like all other problem, I need to find ground reaction first. Again, in any problem related to shear and bending moment, the first thing that you do is to find the ground reaction. So at point A and at point B. FA and FB. I need to replace this loading with one point force, and that point force will be, because it is a triangle, it's going to be 1/3 from the bigger side, so it will be like somewhere here in 1/3 of 3, which is 1, and the amount of it would be, so let me just draw it here. I'm going to have F of A here, F of B here. So the force is 3 times 50 divided by 2. Remember that the force for a triangle is the area under the triangle, and area is half of 50 into 3. I'm going to get 75 Newton here. Distance here is 1, distance there is 2. Again, in this problem, I cannot say FA is equal to FB is equal to half of 75. I need to do my calculation to find the number. So in order to do the calculation, I'm going to go with that equation. Sum of f of x equal to 0, no force on the x. Sum of f of y equal to 0. I have FA plus FB minus 75 equal to 0. Then sum of moment about any point, I'm going to consider A is equal to 0. Then from here, moment about A, the distance for this, again, when the force is in y, distance is in x. And this force is going to go clockwise about point A. So it will be minus 75 into 2. This minus is because it's clockwise. And for FB plus f of B, that I want to calculate it, that distance is 3. Now, if I simplify this equation, I'm going to get f of B is equal to 50 Newton. You move this one up here. From here, you get f of A is equal to 25 Newton. 25 and 50. Now, I like to do, in this case, I like to do one cut. I do the cut at distance x. So let's do a cut at distance x, and then let's see and what we will be ended up at. I have a distributed load, and that distance, I cut it at distance x. The ground reaction here at A is 25 Newton. How much the height would be at distance x? It's not going to be 50. It reached to 50 at the distance of 3 meters. I need to do similarity between triangles to find that height at x. So I'm going to have something look like this, right? At the distance of 3 is 50. At distance of x is how much? So similarity between triangles talk about 50 over this distance, I call this y, okay? 50 over y is equal to 3 over x. If I calculate y, y will be equal to 50x divided by 3. So this distance here is 50x divided by 3, and I can move on. So because I cut it from there, I need to replace it with two things. One, the shearing force V, and then the bending moment M. So I'll do the equation here and solve for V and M. Sum of f of y equal to 0. From here on the y, I need to translate this to another point force. So 50x times this. So it will be half of the base times height. So this will be half of x into 50x divided by 3. So half of that will be 50 divided by 6 x squared. That's what I got. So I got this one would be 50 x squared divided by 6. I put that in the distance of third of x. So this will be 1/3 of x. Sum of f of y equal to 0. I'm going to get from here, I have this force of 50 x squared divided by 6. That's going down is a minus, plus 25, which is going up. And then we have the v, plus v equal to 0. From here, if you solve for v, you will end up v is equal to 50x squared divided by 6 minus 25. That's what I got for the shearing force. For bending moment, we apply the same thing. So sum of moment, I'm going to consider this is point C. Sum of moment about point C equal to 0. Again, v doesn't have any moment because that's on that point. So we have 50x squared divided by 6 times the third of x, and that's going to go positive. Let's put the m first. M plus 50x squared divided by 6 times the distance of third of x. This one, the last one, 25, that's going to go clockwise. So minus 25 into the x equal to 0. I'm going to simplify this equation for m. So from here, I'm going to get m is equal to 25x minus 50x cubed divided by 18. So the time to draw them. So to draw them, I'm going to have the equation for v and x. Next one is for m and x. So 50x squared minus 25. So if you put 0 on this equation, in the beginning you get minus 25. And then this gonna go to, like, this is a quadratic equation. It's gonna go somewhere up, then go down. So I need to find where this thing goes to its maximum, then it's gonna go down. So the maximum of this, or even sometimes I don't go to a maximum, right? I just simply, this function simply go up. So if I evaluate this at the distance of 3, if I put 3 here, so I have 3 to the power of 2, 950 divided by 6 minus 25. At that distance will be a 50. So I'm going to start from minus 25. It's going to go like this to the 50 at the distance of 3. And that 50 actually is this value here, right? That 50 is the value down there. So let's do it for the other one. The other one for the bending moment. Bending moment is this equation. It's a little bit hard to draw this because this is like a cubic equation. Again, you can use a graphing calculator, or there are different ways to do that. I'm going to start from, if I put 0, I'm going to get 0. If I put 3 on this equation, if I put 3 on this equation, I will get a different value. So again, if I put 3 to the power of 2, again, I expect to get 0 if I put 3 on it. I'm just checking my values. Minus 50 times 3 to the power of 3 divided by 18. And you got a 0. So this is going to be something look like this. you can use your graphic calculator to draw that. So again, I'm going to stop recording on this video. On the next video, I will show you different platforms when we have forces in different location rather than where we have them like uniformly on the middle or